Yeah.
All right. All right. Welcome to an intro to HPC talk. Just want to get a quick survey of the audience. How many people here use SSH to log in somewhere? Okay, almost everybody. So presumably use Bash or a similar shell. That's pretty much everybody. Okay, great. So I'm here for your benefit. So stop me, ask other questions. I warmed this over a little bit from the previous talk. I usually give this once or twice a year. And I'm actually working with the Data Science Institute. We're actually going to have a series. And the one that I think you might be particularly interested in is Duncan Temple Lang is going to give a talk on kind of HPC use with R. So if you do anything with R and HPC, I strongly recommend you go to that talk. I might give this talk. It'll be much the same as what you see today. And then there'll be, I think they're going for once or twice a month. For all the Crick users, I have your email address, and I'm going to send out an announcement. If anybody else that's not a Crick user yet, just send me an email and say, hey, Bill, let me know about that seminar series. We've been doing clusters for quite a while on campus, all kinds of flavors, starting back in 1994 when the alpha was the king of the block before digital died, and then compact died. And then HP made some poor decisions. Started slow with 10 clusters over the next decade. First college-wide cluster was College Ag. These days we've got 14 clusters, about 500 nodes. I think I have another. I actually get this question. Generally, it's a head node where you log in, and then a bunch of compute nodes hidden behind it, and then a NAS that you really don't know is there. All you know is your home directory is everywhere you log in. The SGE and LSF have kind of died off. Entirely Linux. I think the points, there used to be one Microsoft on the list that they donated, but even that one's gone. And then another question I often get is, when I'm on my laptop, how much faster will it be? And I recommend, there's some numbers here that are just slightly dated. Things changed about 4 weeks ago. But these are the numbers I look at. Here, which is pretty much 4 to 5 times most metrics you would care about, except for cost. It's only 1.5 times the cost. And then, like the big mem on Crick, the Quad Xeon, quite a bit more RAM, 10 times the performance, 7.5 times the cost. So that, in a nutshell, is why people use compute nodes instead of desktops under their desk or laptops, things along those lines. With that said, if you have a single process job on your laptop, a single process in the cluster may not be any faster. So it depends on a lot of details, but unfortunately I cannot just magically make that thing in your laptop run 10, 100, 200 times faster. They do have many more CPUs, but typically you either need a lot of problems or a program that can use more than one CPU, which even today is not that common. Like Python, for instance. By default, you use one CPU. There are libraries to use to fix that, but there's complications related to using those libraries. Anything with a GUI, with a mouse, you crack on your visualization, things like that, won't run. I mean, they'll run. We don't ban them or anything, but Crick is not an ideal place to run a graphical user interface. If you're setting lots of pixels or triangles, visualization, animations, that kind of thing, they'd run better on a good desktop than a cluster. If you want to pop some graphs to see, is this error converging, stuff like that, certainly that will run great on Crick. And then the other thing is that Crick, all the compute nodes don't have visible IP addresses. They're pretty much separate from the campus network. They can download things from the network, but they're not visible. So you can't run services on them. You can't run a web server, you know, those kind of things. So there's lots of ways to use extra CPUs. It's easiest if you have 10,000, 100,000 problems, easy. I'll show it, it's just a few lines, a couple slides from now. Very easy. If you support pthreads, exec, OpenMP, things like that, which the software developer has specifically added to that application, you can use up to a single node, which on Crick is usually about 24 CPUs. On the big mem, it has 64. If your code supports MPI, which is another level of difficulty, I actually occasionally teach a quarter class on programming with MPI, then you could use the entire cluster, or as many nodes as you can get anyways. So can you take this thing on my laptop that takes 6 months and will prevent me from graduating and get it to run in a day or a weekend or something? Sometimes, but you know, do you have the source code? Can it be customized to the cluster? Does it require a CPU license? I've gotten quotes from MATLAB that were significantly more than the entire cluster cost. So usually people, oh yes, I need it, I need it. Whoa, is that much money? Nah, maybe not. Is it like a sequential problem that where every answer depends on the previous answer, or can it be split into pieces? And you know, like in the previous slides, can it use more than one CPU? Can it use more than one node? And the worst case is it might run slower on the cluster than your laptop, depending on exactly what it's doing. So if you're lucky enough to be developing, thinking that someday you might need resources more than your laptop, I'm not going to read through all this, and the slides will be available, but you should think about it before you write your first line of code, ideally, because how you write it, how you multiply a matrix can be completely different if you're trying to do it on a cluster as opposed to just a code you're running on your laptop. It's, you know, what they call it, not invented here. You know, I don't want to use somebody else's code. Extremely bad idea. And one of those things is never write a message passing library. Do not try to do that yourself. They're very highly optimized, and you'll miss out if you're just opening a socket and sending bytes back and forth. Around 2 gigabytes per CPU. Please run there. You'll get your job will run the fastest. You'll consume the smallest fraction of the cluster. There'll be very little idle resources. If you need 4 to 8 or more gigabytes of RAM for a single process, and I'll show you how to collect that and look that. The big NEM nodes are best. We don't have any GPU nodes on Crick at the moment, but if you have a code that uses CUDA, it can be a pretty big advantage. And like I said before, don't try to do the complicated and then you notice how some CPUs are closer to the PCI bus, so that should be the one used for communication. The latency to memory is different for each one. And the kernels, the libraries, where you are in cache, which page you have, all that kind of thing is why, it's just one of the many reasons you don't want to try to even do something as simple as multiply a matrix. Because the difference in performance you'll find can be pretty huge. So this is a current photo, current machine you can buy in a pizza box. These are memory channels. So each one of those you can say, hey, memory, I need, what's at this pointer? So there's 16 memory channels, 64 cores, 128 threads. And this little red circle is what you get on a laptop. So if you can use the whole machine, you can see a huge increase. But if you're Python by default, will use half of one of these. So it can be not that there are ways around it, but by default. So Crick's one of my mid-range smaller clusters, and so we only really have one of these switches. But this is how it would scale if we added enough nodes. Right now, I think we're 18, 20, 18, 23. So we're at about 24 ports. And at 36, we'd have to buy a second switch. And it's going to cost about $8,000 or $10,000. We need to coordinate among the contributors of the cluster, because we're going to have to add a spine so that the nodes over here can talk to the nodes over there. But fortunately, the network's fast enough that as a user, you don't have to think about this topology. Just figured I'd throw it up real quick. This is a log graph of just accessing something in memory. And so this is like 10, 12 gigabytes a second, which sounds like a lot, but this is a log graph. So if you're more highly optimized, this is factor 2, factor 2, factor 2, factor 2. What you want to be is up here around a terabyte a second. And that's why even, I know I use this a lot, even multiplying a matrix, accessing by row, it's much easier to be towards the top of that. But accessing by column, you're not accessing memory sequentially, and you can really fall down. And there's various ways to do that, but it's a lot of complicated code that you never want to make a mistake in, thus the library. Crick does have an InfiniBand, and it was expensive. We probably could have got a third, 40% more nodes. 103 times faster than gigabit, depending on your message size. Again, I like log graphs. So you can tell for really small messages, it's only a factor of 4. But as soon as you get above, say, 256 bytes, which is a pretty small message, gigabit just flattens out, and InfiniBand keeps increasing substantially. I'm not going to talk. The same thing with latency. I think you get the idea. So WRF is a common. I'll come back to this later. It's a very common weather simulation. You can see that right around here on gigabit, it stops scaling, or it scales very slowly. So going from 9 or 10 nodes to 24 nodes doesn't get you much performance. Whereas on InfiniBand, I should fit a straight line to that, but it's pretty close to linear up to 24 nodes, which is about the size of Crick. So as the clusters get bigger, this is just a diagram of one of my clusters. Who can get an account? I believe anybody here can just fill out this link here if you don't already have an account. Generate a key, upload it to us. We'll create it. So there's actually doesn't look that will be a link when I fix it. That's the link specific for generating key pair, not that you can't just Google it yourself. It's basically simple. You keep the private key where you sit, and you give the public key to me. If you get an email from me asking for your private key, it wasn't me. Share your private key with nobody. And don't put it on any third-party servers. Just ask us. But generally, if you're touching the machine, that's a good place for a private key. If you're not touching the machine, you can do it through the network and forward it, things like that. I'm not going to show the animation for how to log in. You guys have done SSH. So one of the first questions I get, you get on the cluster. How do I get my data, input files, scripts, whatever up? You can SCP straight to the cluster. Don't recommend that for large files, just in case like there's a reboot or a network problem. You like to pick up where you left off. Rsync is better. For anything you type, source code, input files, things like that, I find Git quite useful. So you can just edit on your laptop, just commit, and a lot of the editors actually are integrated with Git now. You just say like sync, and then you can pull it down on the cluster. That way, 3 months, and then suddenly in the last day your jobs start dying. You can like do a difference. Hey, is this script different from the one I ran last week? Show me the differences. Or if it's just totally whatever, you can just throw it away and go to a previous version. You know, human hours are probably the most valuable part of this cluster, and Git's really good at keeping you from losing those hours trying to figure out what went wrong. We also support Globus, especially if you have a large data set, you're working with another research institution, you need some giant files. Globus is designed for that. A lot of the clusters have it. A lot of the campus has quite a few sites. I personally run 6 of them, and it's pretty common. Most people, you just search for the word Globus and the institution name, usually that will find it. So say you're trying to get some research done and you've hit a snag, and you create this request. It says, oh, it died. It's like, well, we have 1,200 users, 14 clusters, thousands of applications. We need a lot more than that, and we'll happily ask you for it, but you're going to have to wait until, and then maybe you'll be asleep and we'll be up, and sometimes this will take days to kind of extract this kind of information. Even just the shortest cut and paste. Every one of those arrows is a critical piece of information. What's your username? What cluster is it? What command do you run? What directory did you run the command from? What job? If you can get us that, often we can fix that as soon as we get to the keyboard. From everything, don't mail us your input files, don't mail us your scripts. We can get to it in place, and we're not going to try to recreate your environment on our end. Just that much. It should be just a couple line cut and paste, and we got 3 people on staff. We try to split our schedules. We never take the same vacation days. We try to have really good coverage. So Crick, mostly purchased in 2014. The head node, please don't run any simulations on it. Like if it's for a minute or 2, you want to check if it works, fine. But if I get an email saying, hey, it's kind of slow, and I look and there's something running for an hour, the job will be killed. And if you're using so much, you're actually threatening the cluster, I'll kill it and lock your account and send you an email and say, please don't do that, and acknowledge this before we turn you on again, so we don't want the cluster to die. Somebody could have a job running for a month. If you abuse the head node hard enough, it could cause serious problems. 18 compute nodes with 64 gigs of RAM, the InfiniBand, 2 big MEMS, 3 file servers. This third one is pretty small, and this is for neuroscience, but it has lots of free bays. So as soon as you guys decide to add more disk space, there's bays waiting to be populated, and you'll only have to pay for the disk space. There are no backups. So don't put anything critical. You got your thesis on there or something, make sure it's somewhere else as well, or make special arrangements with us. We'll happily integrate with the server you run, a cloud service. That's not me. Oh, it's me. Sorry. We're happy to help you back up, or you can buy disk space from us and we'll back up, or use a cloud service, anything like that. But it's designed to survive a disk failure, but not a typo. Like you can easily overwrite your own data. And like I said, those human hours are the valuable ones. So if it's in Git, you just pull out the last version, but unfortunately. So everybody gets an account that's part of a group. They just have to ask, they get a group directory. That's what they are today. There is one trick. You can't do that if they haven't been mounted recently. I won't go into the reasons, but if you know it's there, just say cd/group/Dawson Lab, or all my readers off. Sorry about that. So if you install something in your home directory, great. But ideally, you don't run out of somebody else's home directory. Because then a month later, when they change something, your jobs will break. So you can just say, hey, Bill, or help at CSE, please install whatever it is, and we'll install it. Or you can install it in your home directory. Or if you want to collaborate, move it to /group something. You can have a directory for each application, or input files, or scripts, those kind of things. They should be in /group. And the way we make it is that anybody in the group can make a file there, but you can't delete other people's files. And you can work with, if that doesn't fit the way you work, just let us know, we'll change the permissions. But generally, if somebody has a lot of data in their home directory and you're running jobs against that data, we'd like it to have in the group directory. And then it's a little more visible to like, oh, how often should we update it? Do we need to make a job that downloads the new genetic data once a month, or whatever those kind of things are. Do not hard code paths. We may change any path in the file system at any time, but we try really hard to make sure the modules are perfect. So if you say module load, blast, just use blast. Don't try to hard code this in. And if you don't want the version change, we can handle that. You can say module load blast /2.1, and then you'll get version 2.1 forever. If you say module load blast, you'll get the newest one. But even if you get the newest one, we always output it, because it's not research unless you reproduce it, right? And to be able to reproduce it, you need to know what version you have. And so that's why we actually modify the module command to always output the version you used. I strongly recommend any source code in Git. I don't know how much software development is going to be happening on Crick. And like I said, do not assume backups. So if you run this is not specific to Crick, although it looked very similar. Oh, there's no GPUs on Crick. But generally, mix means that some of the CPUs are idle and some of the CPUs are used. So if you have smaller jobs, they probably would run right away. If you ask for a complete dedicated node, it wouldn't run, because there's one node that I was working on, 48 are partly used, and 6 are allocated. So there's none that, I should have had one that said idle. So there are a lot of cases where if you ask for 4 or 8 CPUs, it'll run right away. But if you ask for a completely idle node, you might have to wait. So sometimes it's faster to have a slightly smaller job. So that's the sinfo command. That's probably one of the first Slurm commands. SQ, these are, when you're submitting a job, it's kind of nice to see what's already running, so when you know when to expect and what kinds of other jobs are there. And like these 2 jobs have been running for 36 days. And then a bunch of these are 7 hours, and then that top one is not run yet. And so that's where when you submit a job, you end up in the queue not running, and then it'll kind of fill you in wherever the resources are. And that can give you somewhat of an idea of when your job will run. And to submit a job, any script, you take any command, you can type the command line, you put it in a file, and you just say submit that file name. It gives you a job number, and then that's how you find it in the list. You can also cancel a job by the number. The Crick has the 3 main, these 4 partitions are on Crick. So if you have 100,000 1-hour jobs, the load partition is great for you, because your job can shrink and grow over time based on free resources. And if a node gets busy, it will just kick you off that node and run you somewhere else. So transparent to you, your jobs may, 10% of your jobs may be killed, but if you only lose an hour of CPU time, who cares? As long as you're getting lots of progress. But if you're running a month-long job, running in low would be a terrible idea, because you'd probably never finish. Once a week you'd get kicked off, and you'd never make progress. Medium, instead of being kicked off, you're just suspended. And that's good for, jobs that are, days or weeks long, but that use typically less than a node. Because if you use more than a node, you wouldn't want part of your job to get suspended. Most jobs wouldn't like that. And then this high priority is where we have that promise. If you buy 4 nodes, we'll give your group 4 nodes within 1 minute, no matter what the cluster is doing. But the flip side is you can only run as much as you contributed. So this is a great way to get more than you paid for. If there's 16 nodes free, you can run on all 16 nodes. That's true for lower high or lower medium. But on high, you can only get what you paid for, because I can't make that promise to you without impinging on somebody else's promise unless people only run on what they pay for. And the big mem's pretty obvious. Best place to run large jobs. So your first script, very simple. By the way, where'd my thing go? That -L right there is very important. It loads some of the infrastructure related to the modules, and nothing works if you skip it. But, very simple echo command. Srun is just something from Slurm that basically is telling Slurm that this is just part of your job. And it allows, I'll go over it later, but it lets you analyze the performance and the resource utilization a little bit more closely. And just sleep hostname. This is something you could run on the shell. I don't see a whole lot of laptops here, but you could run the same command except for the srun on your laptop. You have to make it executable, and then you say, hey, Slurm, run this script. If you say SQ, you see that you're on it, and you landed on this node. And then I ran SQ again, and it's not there anymore. It finished. There's also an option that I think I'll go over later. It's very easy to have it email you, so you don't have to track. You can run 100 jobs, and if 10 finish, you'll get 10 emails when they finish, that kind of thing. So I just run ls, and by default, it's just whatever you call the script and the job number, which you'll notice is the same one that you got up here. And then I just cat that file to see what's in it, and it says module load, that loaded. Hello world, I'm running on node C231. So that could have been an R script, MATLAB script, a bunch of shell commands, uncompressing files. Whatever application you ask us to install can be run right there. I don't know. I think I might skip this. OpenMP basically lets you use more than one CPU on a node, but does not scale well. So you're very rarely on a 24 CPU machine are you going to get 24 times faster with OpenMP. It is very simple. Actually, that's a good question. How many people here are going to write code, plan to write code to run on Crick? Just 1, 2, 3? So you can follow up with me directly on the software development side. So we really want to protect the head node. Because the head node's down, the cluster's down, everybody's very unhappy. But even if you want to run R and you're just going to be doing some simple stuff for 10 minutes, it's as easy as running that command. So it's still interactive. You get a prompt, you can type in commands, anything you could do, but this R is running on a compute node. If you crash the compute node, I don't care. I would like to know, hey, Bill, I think I crashed C231. Sorry, I didn't think I was using that much memory. No problem, we can remotely reboot it. It'll be available again in a few minutes. Not nearly as big deal as losing the head node. You could actually just run bash here, but when it's this easy, you might as well just be on the head node, running commands on nodes as needed. But if you prefer, you can just, instead of R, you can say bash. And then you have a shell, just next shell will actually be running on that node. And then your file directory's there. They really shouldn't notice any difference. The only difference you'll notice is if you crash it, the head node's still up. So here's a really simple job to run R based on this. It's just going to load this small R test script. And again, I just use the srun. It's not mandatory. but it does make it much easier to tell what's going on if something weird happens. So ideally, every command that's going to use much CPU or RAM or I/O, just put the Srun in front of it. It works just exactly, except for that, you won't be able to tell that it wasn't there. You'll just, R will run just like you normally expect it. Same thing for MATLAB. The module load MATLAB sets up the environment, and in your script, it will say, MATLAB R2016A loaded, so that when you look at your output file, you can tell what version. So let's make this a little bit smaller. There we go. So say you have 90 input files. You want to run it through R, MATLAB, something else like that. Don't write 90 scripts, and don't put a for loop in this script saying run this one command 90 times, because either you'll run it 90 times sequentially, so it takes 90 times as long, and you'll ignore the rest of the cluster, which is kind of silly. Or you'll have to ask for 90 times the resources, and then you might never run, because there might not be a large chunk of the cluster that's free. If you just do this, if there's one CPU free, it will run. If there's 50 CPUs free, it will run. If the head node reboots, you're still running. It's a very robust and scalable way to take an arbitrary amount of input with a very simple script. There's not a whole lot to keep track of. It's very simple. And then this could be 1 to 90, it could be 1 to 10,000, it could be 1 to 50,000, whatever. And it just simplifies things. And it also makes Slurm happy. You're very efficient at using resources. And unlike pretty much all other ways of using Slurm, the job can actually shrink and grow over time. So it's fairer to other users. And assuming this is only running for, say, hours, I'd run it in the low partition. If it's running a week for each one, which is fine, I'd use either medium or high. So you submit a job, and it lands on C231. You can SSH to C231, and then just run top. And for the first time you run the job, I recommend this every time. So if this is much higher, your job is doing nothing but I/O. And if it does that for a few minutes, that's fine. If it does it for a few hours, you might want to talk to us about how to optimize the access to the file system. You might want to use local scratch. Maybe we should host your data set if it's going to be used a lot actually on the compute nodes. This is also a number that, you notice how this number divided by this, this number is very small, less than 1% of that number. So that basically means you're using close to zero swap, which is great. Because swap is thousands of times slower than RAM. If you're using swap, something's wrong. You need to ask for more memory, split it across more CPUs, or maybe run on a big mem if you're not already running on a big mem. So this is good. If each of your jobs is using 100% of CPU, the bottleneck is not elsewhere. And then this 2.8% is just good for you to know. Once it gets above 3 or 4%, since there's either 24 or 32 CPUs per node. So if you didn't ask for more RAM and it's much higher than that fraction, then you need to ask for more RAM. So if you want 16 gigs of RAM, which is 25% of a node, if you see a 25% here, you should have asked for 16 gigs of RAM. It's 50% here, you should have asked for 32 gigs of RAM, those kind of things. But if that's true, you'll see the swap going up, and then as you swap, the CPU goes down. So this is just a good spot check. So like I said, the default job size is 2 gigabytes or so, depending on the details of your node. And then this is the way you ask for more memory. You just say -mem equals megabytes. Or if you, on a multiple CPU job, if you prefer, there's megabytes per CPU. And these two numbers are about the same. It's annoying they use different units, but if you see resident much smaller than virtual, that's another sign of swapping, and that's on there. So if you're running that same job, you don't want to use top, and especially if you're worried about I/O. This little script, people keep changing it, so we're happy to write a wrapper script, but it seems like every time we give it to somebody, they make a little tweak to it. But basically the point here is, you see early, in the first 10 seconds, almost no I/O. 600 megabytes is not much. 10 seconds later, we're at like 3 gigabytes. And 10 seconds later, we're at 6 gigabytes. So 6 gigabytes isn't a terrible amount, but if you're running thousands of these jobs, and especially if you're running hundreds of them at the same time, you might be spending more time waiting on I/O than you are from actually doing a job. And if it's running slower than you expect, or it's crashing or things like that, how much memory you're using and how much disk you're using, especially over time, can be really valuable. And if you ask for more than you need up front so it doesn't crash, this is how you can know how much you actually need, so you can go back. Like say you ask for a whole node, 64 gigs of RAM, and you only use 10%. You can look at this, and an hour later, whenever your job is done, now you can run 10 times as many jobs in that same node, because now you know how much RAM it's using. Running top is fine too, but for some jobs, like they'll run for 3 days, and their memory use is like highly variable. And so that's when I recommend something like this, because then you don't have to watch top for 3 days. So one of the things we do to help reduce the I/O is the NFS shared file servers are, of course, shared. And so if you're hammering it, it becomes a big bottleneck. And so if you stage your files to /scratch, that's per node. So you're not sharing that with any of the other nodes. It can be substantially more efficient. And so basically what I'm doing here is I just, it's /scratch on each node. That's your username, and that's your Srun job ID. Because you don't want, if you run 10 jobs, you don't want them overwriting the same files in /scratch. So I just make the directory, I exit if it fails, I make 2 subdirectories, I untar this file that has 50,000 files on it, and now this binary can run and have my own copy of 50,000 files. So even if you're doing something very I/O intensive of it, you're not going to be bottlenecked by the central file server. But you do need to clean up. Or otherwise people will say, hey, I tried to run my job and Scratch is full. And then I'll see who filled it up, and I'll send you a mail saying, hey, could you clean up after your job? I wouldn't bother with this until you know I/O is a problem, or if you're just really sure you're going to do a ton of I/O. But when that does happen, this is exactly what you'll need to do. I don't know how many large MPI jobs people plan to run, but if you're going to use a lot of resources, you really should get to know your job well enough so you know exactly how much to ask for. And one of the things here is that if you're at this point, you're going to get about 27 gigaflops. But if I ran 2 jobs, I would get this on the first job, and I'd get this on the second job. So I'd get 42 gigaflops. So I've almost doubled my performance by just not trying to, this runs in 3 days, and this runs in 2.75 days. That's not a very good use of twice as many resources. So, if you're RAM limited or CPU limited, getting those resources you use to the appropriate number can greatly increase your throughput on the cluster. I know it's tempting. I'll just pick the biggest. I think I can get 22 nodes right now. Let's run. You've greatly reduced the efficiency of the cluster, and you're denying it from other users. And when you deny it to other users, when they don't run their jobs, they'll submit their jobs, and next week when you want to use the cluster will be busy with their jobs. And so it's best for everybody to be reasonably efficient in use of the cluster. So you say, hey, Bill, install some app. And we'll reply, typically saying something like this. Oh, to get that to work, say module load, those. You notice how each version is there. So a year or two from now, you're saying, hey, Bill, somebody challenged my published results. I want to reproduce them. How can I reproduce this from 2 years ago? Well, if you saved your output file, there's a good chance we can reproduce it. If you didn't save your output file, we don't keep track of, because we have thousands of modules, and they change every day. So figuring out what combination was used without your output would be very difficult. We generally don't delete modules, but unless they're kind of actively causing damage. If you notice how there's no versions up here, if for whatever reason you know that 3.2 causes a problem for your code, or you just prefer those options, or you want to compare to a run you made last year that used that version, you want to use the same version today, you just say, HMMER/3.0, and then that will stay the same. These are all good. I don't know. I guess so never write to the same file for more than one node. That's a great way to corrupt it. And the worst thing is when you test it, it will probably work. But when you have more nodes running over a long period of time, there's very likely to be a truncation, an overwrite, a corruption of some kind. And it's very easy to do in a cluster, but NFS isn't magic. It's kind of loosely coherent. So if you have a bunch of nodes trying to access the same file, for read, it's okay. For write, it's not good at all. A bunch of resources. That's pretty much it. So any questions about anything I presented, anything to do with HPC, anything to do with Crick? This is, this will be available. I'll send it to Russ. This is basically all you should need to be able to start running things on one of our clusters.
You have shown an example how to specify how many nodes you want to allocate to the job. Is there also a way to specify how many CPUs you want to allocate?
Nodes is big N, and CPUs is small n. But that does bring up one complication. So if you want a Python script to use 4 CPUs, but you want Python run once, use -C. So -C4 would run Python and allocate 4 CPUs and just run Python once. If you want it to be run 4 times, you use the small n, you say srun Python, Python will be run 4 times. So like MPI jobs, you actually want to run it as many times as the CPUs you want. And then you can even use them together. Like say you want to run 4 copies of Python, but give 4 CPUs to each one. You'd say -C4, -N4. But if you want it on the same node, because the problem is, that, like say, if you ask for 16 CPUs, that may or may not be on more than one node. So if you say -N1, you'll get 16 CPUs on a single node. So the 3 ones, capital N, C, and small n, let you play with that. And I didn't go into this more advances, but if you have a more complicated pipeline, you can actually ask for a chunk of resources, then use only a small piece of it for each stage in the pipeline. So you don't have to, like it's better to, instead of like reading 100 gigs and running something on it and writing 100 gigs and having the next stage do that and the third stage do that, you can actually set up pipelines where you say, okay, 4 CPUs will be producing it, 4 CPUs will be consuming it, 4 CPUs will be post-processing it, and then you don't have to write all those intermediate files to the file system, and then you're not idling